All right, so we are beginning our final section in this particular packet. All right, and that is translating real-world expressions. So go ahead and set up your workspace if you haven't yet done so. Pause when needed, but let's jump right to it. All right, so this final piece of the puzzle right here, we basically want to, I'm going to move this up here because this kind of goes up here more so. We're really more writing expressions again. Okay, we're bouncing back to that skill. In this one, though, we're doing it in a real world context. All right, so it's going to be a little bit more contextual. We're going to have to make sense of some situations and write variables related to that. We are on our final section right here, real world application of this skill right here. Now it's going to bring in a lot of things. We've talked about properties, we've talked about evaluating expressions and knowing the order of operations. So this is kind of bringing it all together. So we have to kind of be able to summarize that. Let's jump right to the first part here. All right, translating expressions. Expressions are frequently used in real life to describe situations involving comparisons. Okay, we do this a lot. Pause if you need to write that down. When translating verbal descriptions to algebraic expressions, we need to ask ourselves a couple questions. What is it that's being compared? And what will the variable represent? Again, a variable is what it is because it can change. It can vary. That's where the root word is right there. It can vary. It can change, and we can substitute different numbers and see what happens. So a lot happens when you have a variable in a problem. So let's look at these first few examples together. Write an expression to represent the comparisons below. Simon has 4 more cookies than Lucy. Now, we know something in this sentence, and there's also something we don't know. So let's start with A. Lucy is represented by, let's use L. L because of her name. We'll use that as our variable to represent Lucy's amount. How can we explain the number of cookies that Simon has, though, compared to Lucy? We'll go back to your sentence here. Simon has 4 more cookies than Lucy. So if you think about what Lucy has, Simon's is 4 more than that. So if Lucy has 2, Simon has 2 plus 4. If Lucy has 1,000, then Simon would have 1,000 plus 4. So if we want to show this with an expression, Simon's total is equal to, any guesses? Lucy's total plus 4. Okay, so we can just show this with an equation. Now I could even have just used S equals Lucy's plus 4. S equals L plus 4. But we want to be able to start doing this because in this sentence, there was something we knew and there was something we don't know. We don't know what Lucy has. We just know that Simon's is 4 more than that. All right. So let's look at number 2. Gary weighs 12 pounds less than Jeff. Again, there's something we know and there's something we don't know. So think about those 2 variables. One thing we know, one thing we don't know. So Jeff would be represented by J. J for Jeff. We'll just use that as our variable for Jeff. And we don't know what he weighs, though, but we do know something about Gary. We know he's 12 pounds less than Jeff. So think about Jeff's weight. How now can we explain the number of pounds that Gary weighs compared to Jeff? Well, if he's 12 pounds less than Jeff, that would be Jeff's weight minus 12. Gary's weight is equal to Jeff's weight minus 12. All right. So we're taking what we know and we're creating expressions to show it. Now, it would be more helpful if they gave us Jeff's weight or if they gave us Lucy's number of cookies, but they don't always do that. And you have to be able to understand what's really going on in a problem. And that's why we're going to use variables to show some of these things. Variables should represent the part of the situation which you are given the least amount of information. Like here, we weren't given Lucy's number of cookies. We weren't given Jeff's weight. That was the least amount of information we were given. We were given more information about Gary and more information about Simon, but we used variables to show what we really didn't know, okay? So if I look at this right here, practice defining a variable and translating the verbal expression to an algebraic expression. So number 3, the width of a box is twice as long as its length. Now I know something about the width, but I don't really know much about the length. So if I define a variable, the first thing I would say is let's let W equal the width of the box, okay? Because we know something about it. We know that it's twice as long as the length. So the length then, we would just use L for length. So if the width is twice as long as its length, well, what happens if we have twice L? If we have double L? That kind of tells me that the width is the length doubled, or 2 times the length. That's a summary of what's going on here. The width can be W, but it's equal to double the length. All right, that's what this sentence up here said. The width is twice as long as its length. In number 4, the 80 brownies sold at the bake sale were half the number of Rice Krispie treats sold. So first, let's define a variable here. Let's start with R, the number of Rice Krispie treats. Okay, that's kind of what we have some information about it up here. Now, the number of brownies is really half of that number. It says right here, the 80 brownies sold were half the number of Rice Krispie treats sold. So if I know how many Rice Krispie treats were sold, the number of brownies would be half of that. So 1/2 times R. And again, when you put them side by side, you're multiplying this value, or the coefficient, times the variable, R in this case. So represent the number of Rice Krispie treats. Well, that would have just been R. Okay, if R is the Rice Krispie treats, that's what R would stand for. In number 5 down here, Allison sold 12 more boxes of cookies for the fundraiser than Evangeline. So let's start with what we're kind of working with here. E would be the number of boxes Evangeline sold. All right, that's what we don't really know. We don't know much about Evangeline. We do know, though, that Allison sold 12 more than her. So Allison's would be Evangeline's total plus 12, in essence, okay? Whatever Evangeline sold, it's 12 more than that. So if she sold 10, well, now Allison sold, 10 plus 12. If she sold 2, then Allison's total would be 2 plus 12. So we don't know this, but we know Allison sold 12 more than that. So that's why we're starting with our variable, and we're thinking about what Allison did. Well, Evangeline would have just been E. Okay, that's what we were showing to represent her. And that would have been however many boxes she sold. Number 6, Xavier's 85 on his math test was 37 points less than twice his grade on the English test. That's kind of crazy. That's an interesting way to think about a math test score, if you ask me. But first, let's define what we don't know. We know his math score. What we don't know is his English score, though. So let's start with that. Let's define that as our variable. His English was his grade on the English test. Okay. So we know the math one, though, was 37 points less than twice his English score. So this gets a little interesting. His English score doubled. -7. I feel like that's incorrect. I feel like this should be 37. Yeah, this should be 37. So don't copy the 7. It should be double the English score -37. And that would be how to represent his math score. His English test, though, that was just simply E, okay? His grade on the English test. So if we're looking at situations, we need to be able to understand how to represent them. We need to understand what we know and what we don't know. And that's what helps us define our variables. I want you to try 7 through 10 right now, and then pause it when you've given it a shot and come back and see how you did. All right, see how you did. For number 7, what we don't know is we don't know the number of people that are skating. So that's your variable, and then you can work from there to figure out the cost of n number of people. Well, it's $100 to rent the skating rink plus $8 a person. So 8 times the number of people. And if there's 36 people, well, now it's 100 plus 8 times 36. and we should end up here. For number 8, they have $365 in his savings account, and he spends 32 bucks per week. Well, what we don't know is the number of weeks that he's spending $32 per week. We know what he has in his savings. We know what he spends per week. We just don't know how long he's done this, how many weeks. So set your variable for W equals the weeks. And then amount in his savings after W weeks, well, what he started with, 365, minus $32 a week times the number of weeks he did that. So there's our expression. And now we can plug in a number, because now they're saying the amount in his savings after 9 weeks, well, that'd be 365 minus 32 times 9. And 32 times 9 would be somewhere close to 300. So really, if I do this minus something close to 300, I get 77 bucks. Check 9 and 10 also if you haven't yet done so. All right, so if I were to summarize this lesson right here, there's really 3 big points. 1, expressions are mathematical statements. They give us information. They help us summarize what's going on mathematically. So expressions are mathematical statements. 2, an expression can include letters that represent a number. We are using variables pretty commonly right now, and sometimes they represent things that we are not sure of their value, but they represent numbers. And the third thing, they are used in real life to represent a process, all right? Because there's a lot going on with some context and some problems where we use that kind of thinking to show a number which might be changing or which might be unknown, but that's what variables help us do. They kind of hold a place of some information, all right? So if you need to write that down, keep going, but pause it. All right, so this is the assignment that goes with it. I want you to give this a shot, and then we'll talk about this later.